All right, let's start with some theory today. So our unit is on polynomials. So we start with an f of x that can be written in this shape. It's a polynomial function. We've already talked about the remainder theorem. That says if you take a polynomial and divide by something of the structure x minus a number, then you get a remainder that coincides with plugging that number k back into f of x, right? So you say r equals f of k. Then there was the factor theorem that says if you get a 0, so if you have a number that you plug into f to get 0, then you get a factor x minus k, where that number k is the 0. Okay? So we use these in conjunction to say if you do synthetic division, happen to get a remainder of 0, that means you have found a 0, so k is a 0, and then you can use this to say x minus k is a factor, which then means you can rewrite f of x as the factor that you found times the quotient, and this quotient is another polynomial. So that's where we left off in 2.3. Now we have two new things. This is what we call an existence theorem. So it doesn't tell you how to find something, it just tells you that something exists. It is the fundamental theorem of algebra. So it says if you have a polynomial with degree at least 1, then you are guaranteed at least one complex 0. It doesn't tell you how to find it, but it tells you that it is possible to establish this and therefore find a factor. Which means if you can do that, get a factor, and you still have a polynomial left over, then you can apply the fundamental theorem of algebra to that quotient and get another 0, which means you get another factor, and you can keep doing this until you have no more zeros. That logic leads to the linear factorization theorem, which says you can take any polynomial and factor it down until you have this coefficient in front, which matches the leading coefficient, multiplied by all of these linear factors, where each of those c1, c2, all the way up to cn represent the zeros of f of x. Okay, so that's the theory. Let's see if we can do an application question. All right, so here we have a polynomial function f of x. And let's say we would like to factor f of x. Okay? So we look at the theorems we have, and we say, okay, what I want to accomplish is this type of factorization, which means I need to find the zeros. Fundamental theorem of algebra guarantees that I can find at least one 0. So what we want to do now is use the remainder theorem to find the 0. So this is how it works. I'm going to take the coefficients, write them down, and I'm about to perform synthetic division. Because if I pick a number in this box, that represents the k down here. And if I can guess a number that gets me a 0 remainder, then I can use this to say 0 equals f of k and use this to find the factor, right? That's how it goes. So I'm going to cheat. I made this problem, so I know the numbers that are going to work. So I'm going to guess the right number straight away, 1/3. So the 3 comes down. 3 times 1/3 is 1. You add those together, and I get 0. 0 times 1/3 is 0. You add them together, you get negative 18. Negative 18 times 1/3 is negative 6. You add these down, negative 12. Negative 12 times 1/3 is negative 4, and you get 0 remainder at the end. So we are successful. Okay. So to understand what we have just done is we have taken f of x and we have divided it by x minus 1/3. Yeah. And what we got as a result is we got a quotient of 3x cubed plus 0x squared minus 18x minus 12 and a remainder of 0. Okay. That's what this part tells us. Now, as a result, because we got this remainder of 0, we can use the remainder theorem to say, oh, I see. So f of 1/3 is equal to 0, right? 1/3 is a 0 of f of x. And then we can turn around and say, by the factor theorem, once you have discovered a 0, you know that there is a factor. So you know that x minus 1/3 is a factor of f of x. Now, as a result, what can you do? Now you can take f of x and rewrite it according to this logic as the factor we just found. So x minus 1/3 multiplied by the quotient we found, which synthetic division found the quotient for us. That is this part right here. So we would write this as 3x cubed minus 18x minus 12. Okay, so we've gotten somewhere. But this still does not look like that, because that looks like they've broken it all the way down into linear factors, which means there should not be x cubed or x squared or any of that business. So here's what we say. We say, well, look at this part right here, just the quotient. That's a polynomial, which means that polynomial has at least one complex 0, which means we can apply the remainder theorem and the factor theorem again to just the quotient. Let's see what happens when we do that. So we're trying to take this quotient that we got from this first synthetic division and find a 0 of that quotient, which means do synthetic division again and try to guess a number in the box that produces 0 for the remainder. But once again, I made the problem, so I'm going to cheat, and I'm going to use a number that I know will work. The 3 comes down, multiply by -2, add them together, multiply by -2, add them together, multiply by -2, and I successfully get 0 remainder. So, what just happened? We took the quotient q of x, which was this part right here, and we divided that by x minus -2, so x plus 2, and we got a new quotient, 3x squared minus 6x minus 6, with 0 remainder, right? This 0 remainder from there. Now, that, by the remainder theorem, tells us that if we plug in the number -2 into the quotient, so we can write down q of -2, and that comes out to the remainder, which is 0. Okay, that part's good. So therefore, -2 is a 0 of the quotient. But what we would like to ask is -2 also a 0 of the original polynomial f? The answer is yes, and here's why. Because remember, f of x, in the last step, we were able to break it down into the quotient multiplied by the factor x minus 1/3, right? This was the deal. And so, if I can plug -2 into here and get 0 for that number, then 0 times anything is 0, and therefore the whole thing is 0. So I am able to say, yes, indeed, this is a true statement. It's very powerful. If you find a 0 of the quotient, you have also found a 0 of the original polynomial, which justifies how we're going to do all these problems. Okay, so from here, we can now use the factor theorem to say, if we have found a 0, then we have found a factor of f of x. So we can say x plus 2 is a factor of f of x, which then means we can write this one more step as x minus 1/3 for the first factor, and then we have another factor, x plus 2, and then we have the quotient after all of this, 3x squared minus 6x minus 6, and there we are. To summarize what we have so far, we have one factor, x minus 1/3. We have a second factor, x plus 2, and we have some other stuff to go. Now, I have two factors written there, strictly speaking because I know from the linear factorization theorem that the number of factors match the number of zeros, which will match the degree of the polynomial. So in this case, I have a 4th degree polynomial, which means I should have 1, 2, 3, 4 linear factors. I found 2. I'm looking for 2 more. This is how it goes. I'm going to look at this and say, isn't this 3x squared minus 6x minus 6? Now, I would like to factor this. So the way I factor quadratics is, why don't I let this quadratic equal to 0? Then I can use the quadratic formula to find the zeros, and then I can use the factor theorem to use the zeros to get the factors. Yeah? So First of all, let's divide everybody by 3. So when I do that, I get x squared minus 2x minus 2. Then I can use the quadratic formula and say x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And then I can keep going. This is going to be 2 plus or minus, that's going to be 4 plus 8, which is 12. So then I get 2 root 3 all over 2, which I can simplify to 1 plus or minus root 3. So I understand these numbers are the zeros of this polynomial, because if I plug those numbers into x, I do indeed get 0, which means the factors are x minus each of those numbers. I have x minus 1 minus root 3, corresponding to the 1 plus root 3 on the top, and then I have x minus 1 plus root 3, right? Because if I take 1 minus root 3, but I take x subtract the whole thing, I should end up with that. So, from here, I'm able to say, we can fill this in now and say this is x minus 1 minus the square root of 3, and then x minus 1 plus the square root of 3. Now, it turns out I'm not done yet, because if I were to take that and expand it out, if you look at the x times x times x times x, I will get x to the 4th. But what I need is 3x to the 4th. And that 3 I need to have right there. Now that 3, incidentally, is the same 3. This is the a sub n. That says in the original polynomial function, if you have an a sub n leading coefficient, then you have to have that leading coefficient out here too. This will properly expand out to the original polynomial. And we have fulfilled our goal to factor f of x. All right, let's try another example. We have a brand new f of x. And we would like to factor this f of x. So same method as before. We're going to attempt synthetic division. And what we're trying to do is guess a number in the box here that will give us 0 remainder, and that will tell us the 0. So last time I cheated, and I put in numbers here that I knew were going to work. But this time, let's learn the rational roots theorem. This is a way that helps us guess numbers. Okay. So it says if f of x is a polynomial with the standard notation, then all of the rational zeros, keep in mind zeros and roots are the same thing, so all of the rational zeros of f have to be of the form p over q, where the numerator of this fraction is a factor of a sub 0, the constant term, and the denominator of this fraction is a factor of a sub n, which is the leading coefficient. Every possible rational root has to be of this structure. Okay? So what that means in the context of this problem, the possibilities for p, so p are the factors of the constant term, which for us, -4. So the integers that go into -4 are plus or minus 1, plus or minus 2, and plus or minus 4. And then the possibilities for q, we're going to say, we need the factors of a sub n, the leading coefficient, which for us is going to be 6. So all the integers that go into 6 are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Okay, so that means the list of the possible rational roots are going to be all the combinations of a number in here divided by a number in here. So 1 over 1, 1 over 2, 1 over 3, and then 1 over 6. Then we go 2 over 1, and then 2 over 2 is already in the list because it's 1, and 2 over 3 is brand new. Then 2 over 6 is 1/3, which is already in the list. Then we go to 4 over 1, and then 4 over 2 is 2, which is already in the list. 4 over 3 is brand new. And 4 over 6 is 2/3, so we already have that in the list. So this list contains all the possible rational roots or zeros of f. which means we're not going to try any rational numbers here that aren't in that list. We already know they don't work. So let's try, from the beginning, positive 1. And fair warning, there's going to be a lot of erasing and retrying here. So we're going to take that times 1, add them together, 2 times 1, add them together, 10 times 1, and then we don't get 0. So we know that the number 1 is not a root of f. Let's try negative 1. Okay, 6 times negative 1, add them together, multiply by negative 1, add these together, multiply by negative 1, add these together, and then multiply by negative 1, and that does not add up to 0. Okay, so we know that negative 1 is not a root of f of x either. So we can cross positive negative 1 off the list. Let's try 1/2 now. So 6 times 1/2 is 3. Then add them together. Negative 20 times 1/2 is negative 10. Add them together. That times 1/2 is 9/2. Now, at this stage, as soon as you get to a non-integer value in this row, you know that you can't get back to an integer value because you're going to keep multiplying by this 1/2. The denominator is going to keep getting bigger. So to see what happens, that's 16 over 2 plus 9 over 2 is 25 over 2 multiplied by 1/2 is 25 over 4. So see how that 2 on the denominator turned into a 4? You just can't come back to integers. So at this stage, I know that it's safe to give up. Okay? So 1/2 does not work. How about negative 1/2? So 6 times negative 1/2, add them together, times negative 1/2, add them together, times negative 1/2, add these together, then times negative 1/2. There's my first 0. So my first 0 gives me my first factor. I know I have x plus 1/2. And now, because we have a 4th degree polynomial f, the linear factorization theorem says we're going to have 4 factors, or 4 linear factors. And then if each of these starts with an x, then we have to put the leading coefficient out in front. Okay, so now because this 6 takes care of any coefficients that might show up in the factors, okay, we can take this and say there's a 2 in common everywhere, and we can factor out the 2, which means we're going to divide every coefficient by 2. Divide everybody by 2, and you can cross this line out. This is the new thing we're working with. Now, the reason this is safe is because in order to find the zeros, you're effectively setting this equal to 0 in solving for x. And when you have something equal to 0, you can safely divide both sides by any constant, right? It's a thing. Okay, now more insight. Now our leading coefficient is down to 3. Used to be 6, now it's 3. Which means in our list of Q, that would be the factors of the leading coefficient, there is no longer a 6. Which means 1/6 is now out of the list. We don't have to try that anymore. Okay? The last thing we tried, negative 1/2. It's possible that negative 1/2 could show up again. You could have a 0 of multiplicity 2. So we should try it, just to make sure. So 3 times negative 1/2, and this is what I was saying last time. Once you get into non-integers there, you can give up, because you're not going to get back to integers. Okay, so we're done with the 1/2 and negative 1/2. On to 1/3. So we go to 1/3. 3 times 1/3 is 1. Add them together. Multiply by 1/3 is negative 4. Add them together. Multiply by 1/3 is 4. Here we have it. We have our second 0, which means we have our second factor. And what we have here, this, we can first of all factor out a 3. So we become 1, negative 4, and positive 4. That's gone. And it's a quadratic, which means we can say that's just x squared minus 4x plus 4, which we don't even have to use the quadratic formula for, because we can immediately recognize that that is that. Negative 2 and negative 2 add up to negative 4, and they multiply to positive 4. So at the end, I can just write down x minus 2 and x minus 2. Or it is more customary to say, since we have a repeated factor, I'll just put an exponent on it there. And that is the full factorization. Now, before we end, just one more thing for fun, right? What if we had gotten to this stage, and instead of writing it down as a quadratic and factoring it, we could have said, let's keep going with synthetic division. let's say we try the number 2 because we know it's going to work. 1 times 2, add them together, and then that times 2 is negative 4. So I know that I have a factor of x minus 2, and this last thing right here, that's my quotient, and that's just x minus 2. So I know my final factor is x minus 2. So once you get down to a quadratic, you can do the quadratic formula. You can factor a quadratic by hand, just the normal way, or you can keep going with synthetic division and see if you can guess something that works. And there we have it.